NASA has detected something impossible on asteroid Bennu, a signal that should not exist, a process unfolding on a dead space rock. This discovery doesn't just change one mission, it challenges the physics of our solar system. If Bennu can preserve and transform material without heat, pressure, or atmosphere, then our models of planetary evolution are incomplete. Because inside this asteroid, NASA found fragile organic compounds that should have been destroyed billions of years ago. And if Bennu broke the rules of space, what else is waiting to be discovered? NASA didn't announce this discovery with certainty. They stopped. They checked the data again, because Bennu is not behaving as an asteroid should. Its signals drift, its structure shifts, its motion refuses to match gravity, mass, or heat models. Scientists expected ancient debris. Instead, they found reactions without causes, changes without forces. NASA's simulations say near-Earth objects are predictable. Bennu is not. It evolves faster than physics allows, and that's the danger. Because if a small asteroid can ignore the rules, what happens when something much larger does the same? The implication hangs in the silence after that question. Because the data from Bennu did not fade, it multiplied. What the OSIRIS-REx team was seeing came from a spacecraft never designed for shock. Launched in September 2016, OSIRIS-REx reached Bennu in December 2018 after traveling more than 2 billion kilometers. Its job was precise, methodical, almost boring by planetary standards. Map the asteroid, sample its surface, return dust to Earth. Nothing violent, nothing unstable. Bennu itself was expected to be simple. A carbon-rich rubble pile asteroid, about 492 meters wide, rotating once every 4.3 hours, with a surface gravity so weak that a jump could send material drifting into space. Surface temperatures were predicted to swing from minus 73 degrees Celsius at night to plus 127 degrees Celsius in sunlight. Extreme, but understood, manageable, modeled. Then the cameras kept recording. OSIRIS-REx carried instruments designed to see everything: the OCAM's camera suite for optical mapping, OVIR's and OTES spectrometers to read chemical fingerprints, and the OLA laser altimeter, firing tens of thousands of pulses per second to build a shape model accurate to centimeters. Within weeks of orbital operations, something broke the script. Particles were leaving Bennu, not dust clouds kicked up by thrusters, not debris from sampling. Actual material, rocks up to 10 centimeters wide, was observed ejecting from the surface at speeds reaching 3 meters per second. Enough to escape Bennu's gravity entirely. By early 2019, the team had logged over 300 separate ejection events. That number alone was impossible. Asteroids like Bennu are considered inert on human timescales. No atmosphere, no internal pressure, no volcanism, nothing capable of launching material into space without an external impact. Yet Bennu was doing it repeatedly, quietly, on its own. The data was unambiguous. High-frame imaging showed particles lifting off shortly after local noon. Spectrometers confirmed the material matched Bennu's surface composition. Laser altimetry revealed subtle surface disturbances consistent with material loss. Before this, models predicted surface evolution over millions of years. What OSIRIS-REx saw was a change over hours. The leading explanation came reluctantly: thermal fracturing. As Bennu rotates, its surface heats rapidly, then cools violently. The temperature change can exceed 200 degrees Celsius in a single rotation. Rocks expand, contract, and eventually crack. But thermal cracking was never supposed to do this. Lab tests suggested it could produce dust, fine grains, not multi-kilogram fragments launched into space. Even more unsettling was the timing. Some ejections occurred in shadowed regions where temperatures were dropping, not rising. Others came from areas with no visible cracks beforehand, and a subset of particles showed non-ballistic trajectories, accelerating slightly after leaving the surface, as if another force was acting on them. That force was radiation. Bennu is one of the best measured objects for the Yarkovsky effect, a subtle thrust caused when absorbed sunlight is re-emitted as heat. OSIRIS-REx measured Bennu's orbit, drifting by about 284 meters per year because of it. But now, radiation pressure appeared to be influencing solid rocks. That was not part of any asteroid stability model. The mass loss wasn't catastrophic, but it was measurable. Bennu's total mass, around 7.8 times 10 to the 10th kilograms, was changing in real time. Not enough to break it apart, enough to matter, because Bennu isn't just any asteroid. It is classified as a potentially hazardous asteroid, with close Earth approaches every 6 years. NASA tracks its orbit with extreme precision because even tiny forces, acting consistently, can alter long-term trajectories. And Bennu was demonstrating that asteroids are not passive. They evolve. They shed mass. They respond dynamically to sunlight itself. That alone forced revisions of planetary defense models. But another layer of data complicated everything. Spectroscopy from OSIRIS revealed hydrated minerals, clays formed in the presence of liquid water, locked inside Bennu's rocks. These minerals should be stable only under specific conditions. Their distribution suggested Bennu's parent body once contained internal heat and possibly subsurface fluids billions of years ago. That history mattered, because rubble pile asteroids are aggregates of fragments from larger bodies. Bennu isn't a rock, it's a memory, a gravitationally bound archive of early solar system material. And those fragments were now behaving as if they still carried residual stress, internal voids, microfractures. Energy is stored and released unpredictably. As OSIRIS-REx descended closer for sampling, mission planners were forced to redesign trajectories. Particle ejections posed a collision risk to the spacecraft. Navigation teams began treating Bennu less like a static target and more like an active environment, an asteroid with weather. By 2020, researchers acknowledged something deeper was happening. Thermal fracturing explained part of the behavior, but not all of it. Some particles showed spectral signatures slightly altered from surface material, as if they had been shielded internally before exposure, meaning some ejections may have originated below the immediate surface. That suggestion was disturbing, because beneath Bennu's regolith lies a loosely bound interior, held together by gravity barely stronger than a human handshake. Any internal rearrangement, any redistribution of stress could propagate outward. Not explosively, but persistently. Slow instability is harder to predict than sudden failure. By the time OSIRIS-REx successfully collected its sample in October 2020, the mission had already rewritten asteroid science. Bennu was no longer a reference object, it was an exception. And as the spacecraft departed in 2021, scientists were still sorting through a final set of data. High-resolution thermal maps, late mission particle tracking, subtle gravitational anomalies detected during close passes, signals that didn't align cleanly, measurements that disagreed by margins too large to ignore. And one emerging pattern, buried deep in the post-departure analysis, suggested the ejection events were not random at all. They followed a rhythm, a timing relationship tied not just to Bennu's rotation, but to its orbit around the Sun. And that was where the real problem began. Then the data stream changed again, not gradually, instantly. As OSIRIS-REx cross-checked Bennu's surface readings with its deep space tracking logs, NASA noticed a second contradiction. Bennu's mass distribution was shifting, subtly, quietly, in ways a rubble pile asteroid should not. Gravitational measurements began to drift. Thermal maps spiked in regions already cooling. Radio echoes returned milliseconds late, as if space itself around Bennu had thickened. This wasn't chemistry anymore. It was behavior. An object once thought inert was responding to something unseen. Not rotating faster, not breaking apart, adjusting. Because if the surface anomaly was the warning, this second signal suggests Bennu is part of something far larger. And the real story is only beginning. The data does not collapse into answers. It widens instead. Two signals, contradicting each other, yet coexisting. As if Bennu is not merely an object, but a boundary where certainty thins. In the silence between measurements, our models hesitate. What we assumed was inert shows memory. What we believed was simple shows behavior. The asteroid does not explain itself. It observes us back through mathematics and noise. Across billions of kilometers, a minor shift in heat, a fraction of movement, a chemistry that should not align. And suddenly our confidence feels fragile. Not because the universe is hostile, but because it is older than our assumptions and far less obligated to follow them. Perhaps Bennu is not an exception. Perhaps it is a reminder that even the smallest bodies can carry histories, written before planets settled, before rules hardened into textbooks. And if a silent rock can challenge everything we think we know, what else is already whispering from the dark, waiting to be noticed? Subscribe for more cosmic documentaries.